Lesson: Autoencoders for anomaly detection. Autoencoders have emerged as a powerful tool in the realm of deep learning, particularly for anomaly detection within the domain of cybersecurity. An autoencoder is a type of artificial neural network used to learn efficient codings of unlabeled data. It achieves this through an unsupervised learning process, where the network aims to compress the input into a latent space representation and then reconstruct the output from this representation. The fundamental principle behind using autoencoders for anomaly detection in cybersecurity is the assumption that the model, trained on normal data, will struggle to accurately reconstruct anomalous data, thereby allowing for the identification of outliers. The architecture of an autoencoder comprises two main parts: an encoder and a decoder. The encoder maps the input data to a lower dimensional latent space, effectively compressing it. The decoder then attempts to reconstruct the original input from this compressed representation. During training, the autoencoder learns to minimize the reconstruction error, typically measured by mean squared error or another suitable loss function. When applied to anomaly detection, the autoencoder is trained on a dataset representing typical or non-malicious behavior. Post-training, the reconstruction error for each input is calculated, and significantly higher errors indicate potential anomalies. One of the key advantages of autoencoders in anomaly detection is their ability to handle high-dimensional data. In cybersecurity, this is particularly relevant as network traffic, user behavior logs, and system processes often generate large volumes of complex, high-dimensional data. Autoencoders can efficiently compress and process this data, making them well-suited for detecting subtle deviations from normal patterns. For instance, in the context of network intrusion detection, an autoencoder could be trained on benign network traffic data. When new traffic data is fed through the network, any significant reconstruction error would flag potentially malicious activity, such as an unauthorized intrusion or a distributed denial-of-service attack. A notable example of autoencoders' effectiveness in cybersecurity is illustrated by Sakurada and Yairi, who demonstrated their use in detecting anomalies in machine operation data. By training an autoencoder on normal operational data, they were able to effectively identify deviations indicative of machine faults. This principle can be extended to cybersecurity, where normal operations are represented by benign behavior, and deviations signify potential security threats. The flexibility of autoencoders also allows them to be applied across various domains within cybersecurity, including fraud detection, malware identification, and system health monitoring. Despite their strengths, autoencoders are not without limitations. One challenge is the risk of overfitting during training. If an autoencoder becomes too adept at reconstructing the training data, it may also begin to reconstruct anomalies, thereby reducing its effectiveness in identifying outliers. This necessitates careful selection of model architecture and hyperparameters, as well as the use of techniques such as dropout or regularization to prevent overfitting. Additionally, the quality of the training data is paramount. If the training dataset contains anomalies or is not representative of normal behavior, the model's performance will be compromised. Furthermore, the interpretability of autoencoder-based anomaly detection can be a concern. While these models can effectively flag anomalous data points, understanding the exact nature of the anomaly or the underlying cause can be challenging. This is particularly significant in cybersecurity, where understanding the context and nature of a threat is crucial for effective mitigation. To address this, autoencoders can be combined with other techniques, such as clustering or rule-based systems, to provide more interpretable results. The integration of autoencoders with other machine learning and deep learning techniques has shown promise in enhancing their effectiveness for anomaly detection. For instance, hybrid models that combine autoencoders with recurrent neural networks or long short-term memory networks have been developed to capture temporal dependencies in sequential data, such as network traffic logs or user activity sequences. These hybrid approaches leverage the strengths of both architectures, with autoencoders handling dimensionality reduction and LSTMs capturing temporal patterns, thereby improving the detection of sophisticated, time-dependent anomalies. In practical applications, the deployment of autoencoder-based systems for anomaly detection involves several steps. Initially, a comprehensive dataset representing typical behavior must be collected and preprocessed. This includes normalization, handling missing values, and potentially augmenting the data to enhance model robustness. The autoencoder model is then trained on this dataset, with careful monitoring to avoid overfitting. Post-training, the model is deployed in a real-time environment where it continuously monitors incoming data, calculates reconstruction errors, and flags anomalies based on predefined thresholds. The effectiveness of autoencoders for anomaly detection in cybersecurity can be quantitatively assessed using metrics such as precision, recall, and F1 score. Precision measures the proportion of correctly identified anomalies out of all identified anomalies, while recall measures the proportion of true anomalies that were correctly identified. The F1 score, as the harmonic mean of precision and recall, provides a balanced evaluation of model performance. These metrics are crucial for understanding the trade-offs between false positives and false negatives, which are particularly significant in cybersecurity contexts where both types of errors can have severe consequences. Recent advancements in the field have explored the use of variational autoencoders and generative adversarial networks for enhanced anomaly detection. VAEs introduce a probabilistic approach to the latent space representation, providing a more robust framework for handling uncertainties and variations in the data. GANs, on the other hand, leverage a generator-discriminator framework where the generator attempts to create realistic data samples, and the discriminator distinguishes between real and generated samples. This adversarial training process can enhance the model's ability to identify subtle anomalies that may be missed by traditional autoencoders. In conclusion, autoencoders represent a powerful and versatile tool for anomaly detection in cybersecurity. Their ability to handle high-dimensional data, coupled with their flexibility in application across various domains, makes them well-suited for identifying and mitigating security threats. However, careful consideration must be given to model training, data quality, and interpretability to ensure effective deployment. The integration of autoencoders with other machine learning techniques and the exploration of advanced architectures such as VAEs and GANs offer promising directions for further enhancing their capabilities. As the field of cybersecurity continues to evolve, the role of autoencoders in anomaly detection is likely to become increasingly significant, providing a robust foundation for defending against ever more sophisticated threats.